get started. So between the release of photons from the cosmic microwave background and the era of galaxy formation, the universe underwent a period of time during which nothing can shine. This is known as the dark ages of the universe. How the universe transited from completely dark to the formation of first generation of stars and galaxies and black holes is at the forefront of current research. Today we are very happy to have Professor Naoki Yoshida from the Physics Department and Cavity IPNU of the University of Tokyo to tell us about this. Professor Yoshida got his PhD from the Max Planck Institute of Astrophysics in 2002 and was a postdoc fellow at Harvard University and then was a professor at Nagoya University. He was one of the authors of Gadget Code. If you work on numerical simulations of astrophysics, you probably have used that code. And he's a world leader in numerical simulation of astrophysical phenomena. Let's welcome him.
Thank you again, and it is my great pleasure to visit Taiwan again. The last time was 3 years ago. Actually, right after I returned from Taiwan to Tokyo, I experienced a big earthquake. So somehow my stay in Taiwan became memorable. And I hope this time nothing happens after I return this weekend. All right. Yes, thank you for Yen's nice introduction. Today, I'd like to speak on the early history of our universe. Okay, specifically, I tell you the basic story from the Big Bang to the formation of the first stars. Okay. This is what I call a missing piece in the history of the universe. Okay. Then I move on to speak about what is the role played by the first generation of the stars, what are their characteristics, and so on. And then toward the end of my talks, I touch on two mysteries in the current astronomy, namely the supermassive black holes and extremely metal-poor stars in our galaxy. Okay. References are given here, and if you get interested in these topics, please read through these, including these review articles. Okay. In the beginning, I know this is a joint colloquium, so I'd like to deliver the forefront research of the modern astronomy. The one example is this called gamma ray burst. So every once in a few days, this satellite called SWIFT satellite detects a flux of gamma rays, high energy photons. Okay. It looks just like this. This is the number of photon counts in this energy range. The typical duration is from 2 to 10 seconds or so. This is literally a sudden flux of gamma ray shower. Okay. And afterwards, if we were lucky, we can point large ground-based telescopes to that gamma ray sources, and sometimes we see this X-ray image called afterglow. So apparently, the gamma ray comes from one direction, and the point becomes bright in X-ray and even optical and infrared light. Okay. So over a year or so, hundreds of these events happens, and it used to be speculated even some nuclear war in other planets were happening and generating these gamma rays. That was back in 1970s or so. Now the modern astronomy revealed that it is actually an event caused by the death of a massive star. A star more massive than 10 or 20 times that of the sun can explode and leaving a black hole at the center. And this black hole can launch a relativistic jet, just like this. This is, by the way, a very nice image. You don't really directly observe, but this nice image illustrates relativistic jets. When this narrow jet points to us, point to the Earth, we observe the flux of gamma in this way. Okay? And because it is so bright, we can detect and observe, even if these objects were located about 13.5 billion light years away. Okay. So this is a really spectacular event that we can observe, even at present epoch, from the ground-based telescope. Okay. This is one nice development of modern astronomy. The next one, there's another type of astronomical observations called sky surveys. And sometimes these sky scientists can find a very peculiar object. One example is this. This faint light, perhaps you can only vaguely see. This is faint, but actually this light is emitted from a very massive black hole that has a mass of about 2 billion times that of the sun. Okay. This is again an image. So the black hole swallows the surrounding gas and again generates some sort of electromagnetic jets. And if this is pointing to us, we can see a very faint light, even if, again, this large object is located at a very distant region, about 13 billion light years away. It is certainly surprising that such massive object existed very early epoch of the universe, but it is even more surprising that we can actually perform a detailed observations of this system. For example, this big plot shows the so-called spectrum. Okay, so this is the light divided into many wavelengths. This is, if we observe today, it typically lies in the infrared band from 1 micron to 2 microns. And then we see characteristic features like these oxygen ions, carbons, aluminum, and silicon, and so on. So apparently this object contains a lot of heavy elements other than hydrogen and helium, already in place around them when the universe was just about 1 billion years or so. So as I explain later, our universe began with a Big Bang with virtually really nothing, no heavy elements and so on. But only within the short time period, these heavy elements, just like stuff like this or your body, are synthesized around these black holes. Okay? So the origin of this very massive black hole and the origin of these heavy elements are very interesting. The mysteries are not only in the distant regions. Even in the nearby universe, this is only some thousands of light years away. So within our Milky Way galaxy, okay. If you like start watching, you recognize this is a constellation Leo. And at the heart of this constellation Leo, there's a very particular star, which when it was discovered or published, it was called a forbidden star. This tiny blue star, which is smaller than the sun, however, has an extremely metal poor content. Okay. So the ion content is actually less than 100,000 times that of the sun. Okay. About estimated amount is like this. I need to explain a little bit more about this. So typically, ordinary stars like the sun, okay, it contains a few percent in mass of heavy elements, like magnesium, ions, and so on. Otherwise, 97% or so consists of hydrogen and helium. So because of these heavy elements, if we look at the sun and take a spectrum, again, different wavelengths, we see these many of these features caused by magnesium, ions, calcium, and so on. In this way, we can know what elements are contained in the sun. But this particular star, let's take this example, HE 1327. This is the number, the star. If we look at the detailed spectrum of this, we see virtually nothing. Only the continuum, perhaps generated by hydrogen and helium. So stars are just like the big ball of gas, consisting of gas. And this particular star looks like there's no heavy element. Maybe only a little bit amount of carbon is generated, molecular lines by carbon hydrogen molecules. Okay. So usually in our Milky Way galaxies, the ordinary stars have this amount of heavy elements, but several of them have extremely low heavy element content. Okay. So these are three exciting discoveries in recent years in astronomy, but even more interesting in that these seemingly different phenomena, for example, prompt emission of high energy gamma rays and emergence of a very massive supermassive black holes and a nearby star, which we can even observe with our usual home telescope, can have actually the same origin ultimately. And this origin might be also related to the beginning of our own existence. To tell you the answer, that is actually the star. Our basic belief is that stars must be there before all of these things happen. And actually, in other words, stars can be seeds or the reasons for these phenomena. For example, this high energy gamma ray burst, this is almost the direct evidence that there was a very massive star in place when the age of the universe was just 500 million years or so. Okay, so this is a textbook cosmic history. As you know, or as you might have somewhere, our universe began with a Big Bang about 13.7 billion years ago. Okay. So this picture illustrates the universe was created and it has been expanding ever since. That's why this picture looks like this widened toward the right direction. Okay. In the beginning, there was only a soup of matter and radiation. But eventually, many things happen as the universe gets cooled by its expansion. Okay. For example, eventually, the hydrogen atoms were formed, and then a number of photons are released that actually we can observe directly even today. Okay. And afterwards, luminous objects such as stars and galaxies, supernovae, and black holes were formed out of these a very simple state. And eventually in the galaxy, planets, and solar system developed, and like ourselves emerged on that planet. So, and then we see these rich structure, rich object today here in our universe. And the modern cosmology tells us that all the rich structures we see today were generated from tiny ripples, like small, even like small noises in the very universe. However, very interestingly, if we use modern telescopes located maybe in Hawaii or Chile or even space telescopes, we can trace the cosmic history back in time over 13 billion years. Okay. Because of the speed of light is finite. If we look at the distant place, it's automatically we are looking at the past of the universe. Okay. In this way, so we are here, and then use a large telescopes, then we can see the evolution of the universe back in time. But only this portion or error about a few million years after the Big Bang, this part has not been observed by any wavelengths, and this remains as the final astronomical frontier. And most of the contents of my talk today focuses on this mysterious period. And toward the end of my talk, I give a prospect for directly observing these dark ages of the universe by next generation telescopes. So in the beginning, after the Big Bang, there was only a sea of light elements and the dark matter, perhaps literally like this, except the color. This color is just my choice, not the universe choice. And you notice these tiny ripples left over from the Big Bang. And these tiny ripples, why I can paint this way is because we can observe the moment of such an early epoch by observing the microwave background radiation even from the Earth. Okay. So this is one of the most recent examples of such observations. This is all sky survey of microwave, and this is really like we are looking at the universe when its age was when it was very young. Okay. By the way, feel free to stop me and ask questions if I am unclear about any of these things. Okay, this is the earliest moment of the universe. If you compare, now I want to talk about the star formation, black hole formation in the next 50 minutes or so. But if we compare how they are occurring in the present-day universe, the typical example is like this. This is a sort of nearby galaxy where there are many stars, newborn stars like this, these bright spots. We know there are many things happening, like nearby supernovae, high-energy cosmic rays are flying, or radiation generated and stellar wind generated by young stars, and interstellar gas, interstellar mediums, highly turbulent, and so on. And seemingly, we just don't want to work on such complexity. Some people like it, but I really prefer this simple state. Okay? So our universe might sound very highly, let's say, physical or mathematical stuff, but just by looking at your eyes, the state is very simple. And this is where I really want to put an effort on, for example, computer simulation to see how things would happen if we realize the early universe, the exact state and the exact density distribution and so on. Okay. All right. Now, the things happens in this way. This is, just imagine this is the diffuse hydrogen gas distributed in this way. In the beginning, they pull or gather together by the action of gravity. So the slightly overdense region gets more attraction by gravity, and then start gathering materials, hydrogen and helium gas. Eventually, they form a sort of network style structure like this, a very complex, even 3D-like structure. And at the very center for this picture, there is a clump of gas cloud about 1 million times that of the sun. That is the first star nurseries, okay, that eventually bears the very first star in the universe. So things so far are very simple. Okay, the early history, a few 100 million years after the Big Bang, is a very interesting period in terms of this. In astronomy, we have now a standard theory of star formation, starting from a molecular gas cloud and a tiny protostar and gaseous disk, and eventually this protostar grows to become a main sequence, a bright star. Okay. Also, starting from these tiny ripples of the Big Bang remnant, we can apply the modern cosmology. Our universe today consists mostly of the mysterious substance called dark matter and dark energy, and some ordinary materials. And these tiny ripples are generated by the early expansion epoch called inflation. Okay. So this early history is where these two theories can, in a sense, meet and makes a very interesting things. So right after this filamentary structure forms, the things looks like this. In this picture, the dark parts are dense regions where the gas get together, okay, and even hotter, like in this yellow spot. Okay. And these clumps, gas clumps, are eventually the stellar nurseries. Typical mass is about a few hundred to 1,000 times. And as you see here, it strongly clusters. The side length is about 100,000 light years or so. This is still a very tiny portion of the real universe. But this is something we believe was happening on average everywhere in the universe. Okay. Once these clouds were formed, the things looks really like this simple picture. There's a gas cloud. Is pulled together by the action of gravity like this, and it has also a thermal pressure. And eventually this thermal pressure decreases because the gas radiates radiation and loses thermal energy. And the main constituents are hydrogen and the helium and trace amount of hydrogen molecules. So this is like a quiz, right? How we make or build a star out of this state. And the answer can be obtained by applying our physical theories and physics. Okay? And our computer simulations performed some years ago revealed that it is hierarchical structure of how a tiny protostar is formed. So there is a filamentary structure, and there is clumps of dark matter, the gravitationally bound system, about 1 million solar masses. At the very center, a cool, dense molecular gas cloud is formed. The size is about 5 parsec. So parsec is about 3 light years. And then finally, at the very center, there is a small newborn protostar, baby star, with radius about 10 solar radii or so. So the nice thing with this computer simulation is that the computing power is good enough so that we can resolve these even solar system scale structure out of hundreds or thousands of parsec regions. Okay, so this is one single calculation performed even like 5 years ago. So in this way, we could show how these initial density perturbations grow to form a protostar. Now the question is, what kind of star this will be? Okay, that is the main question we had over the past years. Now, it is easy to make a question. The answering is much harder. Okay. This is a typical thermal evolution from a cosmic diffuse gas. This is temperature, gas temperature, and gas density. I remind you this density ranges over 20 decks. Okay, this is like log scale. Okay, and these listed processes are microprocesses operating in such a simple hydrogen helium gas. But although this looks like very complicated, but we can still follow directly in one single computer simulation by following, for example, the chemical reactions, the radiative cooling of the gas, again the rapid chemical reaction, and emission of infrared radiation, and so on, up to the point when hydrostatic core, the so-called protostar, is formed in this way. So this is very computationally expensive, but it's feasible nowadays to perform such a simulation. All right, if you are interested in the actual computer program, just looks like it. Of course, this is only a part of it. Okay? It's not all of it. If you get bored with these fancy images, this is not the all side of this true story. The dark side lies actually in its writing. Sometimes in the middle of the night, I need to put in these Einstein A coefficients and so on. So this is a true activity in research. Okay? So technically, I need to implement chemistry, radiation transfer, and gravity, and hydrodynamics, and so on. Okay. Now, once a protostar is formed, the situation looks like this. There is a hydrostatic core, a very small one. The mass is about just 1% of the sun, a very tiny, small object. However, this is surrounded by a huge amount of gas. So, like in any theory of star formation, this protostar grows by accreting, by gaining a surrounding mass. The key question here is how rapidly this protostar can be growing or can be gaining this surrounding gas. Okay. So this nice classic picture tells us about how this star grows, at which rate. But the key question really here is, in the end, what kind of stars were formed from this situation? Because the important things like the lifetime or the final fate of a star is determined almost solely on its mass. Okay. For example, a star like the sun lives over 10 billion years long, and its final fate is a quite dwarf. So this kind of star actually can survive over the cosmic history. If they were born in the very beginning, they should be around in the nearby universe. 10 solar mass stars, it has a much shorter lifetimes, just rough numbers like this, but at the end of its life, it can explode as a bright supernova. Okay? A monstrous star, this kind of star, the number is small, but there exists even in our Milky Way galaxy. These stars have a very short lifetime, about just 2 million years, which is much longer than our lifetime, but in the cosmic history, it's short enough. And they die as even more energetic supernovae. Okay? And one thing to note is these stars are also extremely bright. The stars, like 200 times that of the sun, can shine about more than 1 million times brighter than the sun. So you can see the overall impact of what would happen if these stars of various masses are formed in the dark ages of the universe. Now, there have been enormous effort and attempt to derive the answer. So, because this final fate ultimately changes the overall evolution of the of the gas and the formation of the galaxies and so on. We'd like to know the characteristic mass of the first generation of stars. Okay, and theorists, as usual, said many things. Okay, even within these last 14 years, people said, "Oh, it may be like 100 solar masses. Oh, no, it should be like 1,000 solar mass. Oh, no, it should be like 20 solar masses." So all of these people, professional scientists, have their own theories and indeed fluctuating a lot. And part of the final answer was provided by our research group with Takashi Hosokawa here. The key is that we could also identify the mechanism that ultimately terminate the growth of the star and ultimately determine the final mass. So let me remind you how a star is formed, starting from a molecular gas cloud, a tiny protostar, and tiny protostar grows, and eventually at some point stops growing to become a single star. So the key question here is how and when does such a protostar stop growing? Okay. And to do this, we need even more extensive calculations, including energetic photons. Okay. So here the right movie shows how the radiation is launched from a growing star and generating hot ionized gas bubbles, H2 regions, okay, in this bipolar way. And this cool gas that were actually feeding the star is eventually pushed back or pushed away because these hot regions drives a fast wind from the central star. Okay. If you want to look at the snapshot, it looks like this. This is the temperature structure in 2D plane, and this is density. So here is the hot H2 region, ionized, and there's a strong outflow driven. And there is only, you see, a tiny molecular gas disk. This is really feeding the central star to support its growth. Okay. So by calculating this process, we could identify that the growth of a star is actually really like a competition of this bipolar hot H2 regions and accretion flow, mostly through the molecular gas disk. So when this breaks down, then the star growth stops. Okay. So this is so-called self-regulation mechanism, because as stars grow, it becomes more brighter, and it even strongly stops this gas mass accretion through the molecular disk. All right, this is the end of the result. The vertical axis is the gas mass accretion rate. This is about 0.01 solar mass per year in the beginning. So in about 100 years, the star grows to become just like the sun. Okay? Initially, the accretion rate is very high because the gas temperature is high. But eventually, as star grows, it becomes brighter, and there are many photo processes like photodissociation or gas cloud evaporation and so on. And prior to our work, we had a common belief that this gas accretion or growth continues to even beyond 60 solar mass or so. But because of the feedback mechanisms, the stellar growth eventually drops and almost completely will be terminated when the stellar mass exceeds 40 solar mass or so for this particular model. Of course, this is sort of sample dependent, but for this particular case, we simulated from the very beginning to the end, we get the answer of 43 solar mass or so. This mass range is actually very nice in the sense that let us recall the very peculiar star I introduced in the very beginning, which has a very small heavy element content. Looks like this. For these two of such stars, the observed elemental abundances are like this, starting from carbon to magnesium, silicon, and up to cobalt or so. Okay. These points are observed elemental abundance patterns. And it turns out from the theory of supernovae, only supernovae models or progenitor mass 20 to 40 solar mass can actually reproduce these observed elemental abundance patterns. So simply story is like this. So first, massive first generation stars are formed with the right mass range, and they explode and they expel, they synthesize heavy elements like this. And eventually these heavy elements, together with the remaining hydrogen helium gas, were incorporated